Hey, this is Horner. We're going to look at a couple different things today. This is electrostatics review for the AP Physics 1 test, and we're also going to look at electricity. So you want to have both of those notes out, and here we go. So the first thing is we need to remember what an elementary charge is. Remember, that's just the smallest charge of any isolated particle, and the value is on the back of your equation sheet. So this is actually 1.6 times 10 to the negative 19th, and then remember the unit here is a coulomb. And we use this for the charge on both an electron and on a proton. So sometimes we put E negative and we put P positive. And the charge on the electron is going to be negative 1.6 times 10 to the negative 19th. And for the proton, it should be positive 1.6 times 10 to the negative 19th. Sometimes you'll see this as E negative, and you'll see this one as E positive also. So don't let that confuse you. Now, one thing that's not taught very much, and I didn't really talk about it at all, is what the charge, kind of thinking about whether or not things are fundamental particles or not. That means they're not made up of anything else. So an electron is what we call a fundamental particle. Right now, we don't have anything that we know of that would make that up. However, a proton and a neutron are not fundamental particles. So protons and neutrons, they're composed of something called up and down quarks, and these are what we call fundamental particles. And there's certain ways they find them. They smash atoms together, and then these things come out. So anyway, here's a proton. It's contained of two up quarks and one down quark, and an up quark has a charge of 2 over 3 e. And the down quark is negative, and it has a charge of 1 over 3e. So if you add those two numbers together, so you have to take two up quarks and one down quark, when you add all that together, you get 4/3 E minus 1/3 E, and that gives you 3/3 E, and that is positive E, and that's where this number comes from then. A neutron is neutral. It contains one up quark and two down quarks. So if you take 2/3 and add to it 2/3, but make this negative, then we have 2/3 E minus 2/3 E, and that's equal to 0. So a quark can actually have charge less than an elementary charge because a single quark has never been isolated. They're always found in groups. Like they are in a proton and a neutron. So we know what they would be if they were by themselves, but that never happens. So that's kind of the interesting, weird thing about this type of physics. We call this quantum mechanics. It's very weird. And it takes a really special person to be able to understand it. So let's go ahead and take a look at the next thing. So the law of charges. We know that unlike charges attract and like charges repel. For example, if I have two charges that are positive and they repel each other, then two negative charges also repel one another. So it doesn't matter whether they're both positive or both negative, they will repel. But if you take a positive and a negative, remember those are opposites, and so they attract one another. So just something really simple. The force that we use, that we talk about, and when they attract and repel each other is called Coulomb's law. So remember, Coulomb's law is just Fe, so it is the force of electricity, is equal to K, which is constant, times Q1, which is the first charge, times Q2, which is the second charge, all divided by R squared. We'll talk about what all these are here next. So this is what we call the electrostatic, so electrostatic force, and sometimes it's called the Coulomb force or Coulomb's law. And there's a constant that's on the back of your equation sheet, just like all the other constants are, and this is the constant small k, and that value is 9 times 10 to the 9th, and the unit here is a Newton times a meter squared all over a Coulomb squared. They will give all that to you. Q1 and Q2 are both the charges. And then the R is not the radius. R is the distance between the centers of the charge of the two charges. So sometimes R really is the radius, however, that's really not the definition. So if I have a positive and a negative charge, so this one's positive and this one's negative, if I measure the distance between the centers of the two, then that's what we call R. Remember the universal law of gravity, which is Fg is equal to big G times m1 times m2 all over r squared is very similar to that, except for Coulomb's constant is 10 to the negative 11th, and so we know that, well, it's not Coulomb's constant, it's the universal gravitational constant. But Coulomb's constant, which is that 9 times 10 to the ninth, is about 10 to the 20 times bigger. So the electrostatic force is much, much, much greater than the gravitational force will ever be. So just remember, electricity is always much stronger than the gravitational force is. We talked a little bit about conservation of charge in an isolated system. The charge should stay constant, so it will not change. For example, if we start with two isolated, so let's say, for example, I've got a sphere here and it's +4, and then I also have a -2 Coulomb charge here. What'll happen is if I touch the two together, so if I get them where they come together, so we're going to make them go together here. This is +4 and this is -2. We'll have transfer of charge, and so when I transfer charge, it looks like what I need to do is, in order to get rid of this -2, I need to add 3 positive charges to it. So we're going to reduce this one by 3 positive charges, and so now each of them should have a +1 charge. And that's essentially what we see here. So each sphere does end up with 6.24 times 10 to the 18th excess electrons on it. And we know that because we can say that Q is equal to the number of charges times the elemental charge. So N here is equal to the charge divided by E. So the charge here is 1 Coulomb. We're going to divide that by 1.602 times 10 to the -19th, and we get about 6.24 times 10 to the 18th excess protons. So it's got more protons than it does electrons. The next thing we need to briefly discuss is just talk about how things are charged. So remember, all objects contain both negative and positive charges. It's just sometimes some things have a few more positive or something has a few more negative charges, and so they tend to be charged either positively or negative. But you probably wouldn't want to think of anything being just positive or anything being just negative. It does have some other charges in it, but the net charge can be positive or negative. So remember, we can charge things in different ways. If you rub two things together, so we talked about rabbit fur and a piece of PVC, and then we call that friction. So that's charging by friction. If I touch one charged item to another item, we call that charge by contact. So that's what we do with those two spheres. And then if I place a charge item, so we used to have a rod that was positive and we got it next to, maybe let's say that we've got a balloon hanging here, and we would get the negative charges on one side and you would have the positive charges on the other side. So when we do that, we call that induction. And we know that induction can lead to a couple of different things. One of them is polarization, and that's where you just have a separation of charge and you don't really have a net charge on the whole object. So this side tends to be negative and this side tends to be positive, and so that's kind of like a water molecule. If I have something that's charged, for example, let's say that I have a sphere, I have a negatively charged rod here, and it then pushes the negative charges on this side, which leaves this side positive, and then I take my finger and I touch that. When I touch it, then the negative charges then move down my finger, and these charges go away. So then what we're left with is a positively charged sphere. So we call that grounding because we've taken those charges off. If I was to touch this side, then what would happen is my finger would transfer electrons to this sphere. So that's kind of what would happen as it goes through. That is all about charging. So let's go ahead and take a look at the next thing, which is electricity. So electric current, we know that is the rate at which charges move. And so when we want an equation for electric current, I'm going to write it over here. It's I is equal to the change in charge all over the change in time. So if I know how much charge there is and how much is changing, then I can divide that by the time that's elapsed, and that gives us our equation, which is I is equal to Q over T. So you could solve for charge, you could solve for current, or you could solve for time on this. The units are Coulomb per second, which is charge per unit time. That's also equal to what we say, the long word is the ampere, Uh, that would be an amp, and then we use the abbreviation A, and that's really helpful for us. Conventional current, we always say that's the direction positive charges would flow. So if I have a battery and that battery has a positive side and we hook a wire up to a resistor and then that comes back to the negative side, then we know that current flows in this direction. We know that the negative charges really are the things, so we have the electrons bumping into each other and they drift in this direction. And this causes the current or the flow of positive charge to go in the other direction. Resistance, R, basically is just defined as we have a resistor and it keeps things from flowing. So it restricts the flow of charges. It's kind of like if you would put a net down in water, it would kind of slow that water down a little bit. And our equation for resistance for a particular object like a wire is equal to rho times L all over A. So we need to define what these letters are. Just remember, this thing is called resistivity. And resistivity is a material property. So remember there's a chart for resistivities of different metals. We know that gold is a really good, has a pretty low resistivity, and so it allows electrons to go through pretty well, but plastic would have a really high resistivity. L would be the length, and they use the cursive L on it typically when you see it. And then A is area of the wire. So we've got just a really quick example that you see here. I have 3 different wires. We want to know, let's rank these in terms of their resistance. So if they're all the same material, then we don't worry about resistivity. They're all the same area on the ends, you'll see that, so we don't have to worry about it. So here we can say that resistance is proportional to the length. So the longer the length, the more resistive. So this one has a very high resistance because it's the longest one. This one has a mid resistance, and this one has a very low resistance. On the AP test, that would be P, then you would have to use E, would be here's your evidence, and then you'd have to explain, and you could use this as kind of your explanation, but you still need to write some words. You might even bullet point to kind of go through and write down exactly what's going on. So don't forget to do that on the AP test. The next part here is about electric potential difference. Remember, we just call this voltage. It's what a battery has. It's kind of like a pump, and so it tries to pump charge through that through our stuffs here. So we know that that's the change in voltage is equal to the change in the potential electric energy divided by the charge. So that's what electric potential difference is. So we like to use a different equation. We call this Ohm's law. It's V is equal to I times R. We also know that I is equal to the change in voltage over the resistance. And we could also write this as R is equal to the change in voltage over the current. We know that current is a volt per, we know that voltage is volts, current is amps, and so a volt over an amp is equal to an ohm, and so that would be the unit for resistance. And we're just using Ohm's law to help us with that. There are different circuit types. We can just talk very, very simply about circuits. This is an open circuit where there's no current because the charge can't get all the way through. But we do know that this side has a negative potential, and then everything on this wire would have a positive potential. This instant that we close that circuit, so when we close the circuit, now we get charge that will flow in this direction, and we get a current. So here the current has got to be greater than 0 amps. We're just not sure what it is because we don't have any values. On the next page, this one goes through a little bit, and it so we're going to stop here for just a second. All right, we're back now. My page came up this time. So let's look at another couple of different types of electric circuits. This one we know is in series because there is one loop. So if we were to take our finger and just kind of follow all the way around, notice that there's only one path to go around. This one is two resistors, and then that little sign should be parallel. So these are in parallel. If I go through, notice I have one path all the way through, and then there is the second path. So more than one path, it's in parallel. If there's only one path, then I have a circuit in series. We also need to remember some rules that we have. Kirchhoff's loop rule just says that the voltage in a loop should be equal to 0. So let's say that this is 9 volts and these resistors are equal. So here we would have 4.5 volts that would drop. So we would lose 4.5 there, and then we would lose the other 4.5 volts right here. So 9 minus 4.5 is going to give us a change in voltage equal to 0. So that's the loop rule. All this does is just say also that the current is going to be the same within the series circuit. So one thing that I would write down here is current in a series circuit is always the same. And we know that voltage adds. The other thing we know about this is that resistors in series, so a resistor in series is just equal to the first resistor plus the second resistor plus, and then we just go on and on and on with that. On the other, on the parallel circuit, this one, we know that we can use Kirchhoff's junction rule. We can also use the loop rule and the junction rule here, but this one's a little bit more important for the junction rule because if I start right here at the battery and move up, when I get to here, I see there's a junction. So going into this junction, let's say that I have 5 amps here, then the sum of the two here should also be 5. So this might be 2.0 and this one might be 3.0. Then when I get back to this junction, when I come out of the junction, I should equal 5 again. So that is Kirchhoff's junction rule. And using Kirchhoff's junction rule and the loop rule and looking at how all everything's related, we can then also say that 1 over the total resistance in parallel is equal to 1 over the first resistor plus 1 over the second resistor plus, and then we go on and on and on. So that's the rule that we use for parallel resistors and for series resistors, and don't forget about the Kirchhoff's loop rule and the junction rule because those are super mega important when you have to go through and explain things. Electric power is the rate at which our electric potential energy is being converted to heat and to light. So sometimes that rate at which energy is dissipated in the circuit is also what we call power. The only equation for electric power in the equation sheet is this one, but there are more that you really absolutely positively need to know. I know that V is equal to IR, and I could also say I is equal to V over R. So if I take that V over R and I plug it in for I, I'm going to end up with P is equal to V times V over R. So our new equation is V squared over R. So this is the second equation for power, V squared over R. On this one, we're just going to leave it V is equal to IR. And if I plug the IR in for V right here, this would be P is equal to I times R. And so that's equal to I squared R. So P here is equal to I squared R. And that is our second equation for power. So really important that you memorize these or at least know how to get them from P is equal to IV over to this form. So really important that you memorize these two. This one's on the equation sheet. So a little bit crazy, but that's just kind of how they are on the AP world. Very last thing we're going to do here is we're going to do this circuit problem. And I think what I'm going to do is I'm going to kind of make this a little bit smaller. You've got it in front of you. And let's go ahead and put the values in that they give us. So here we know the total voltage in the battery is 6. We know the first resistor is 1 ohm. We know the second resistor is 2 ohms and the third resistor is 3 ohms. So that makes it very, very convenient for us to be able to do. Remember when we do circuits, we always want to use our VERP chart. So here we're going to do V, I, R, and P, and they want us to find the power dissipated in resistor number 2. So when we get that answer, we're going to stop with the VERP chart, but we need to make sure that we still use the words Kirchhoff's junction and loop rule in my answer and show all my work. The very first thing we need to do here in order to fill out our chart is we've got to start by looking at what the resistance is in this circuit. These two are in parallel. And how do I know they're in parallel? Because if I go this way, there's 1. and then, oops, here is another way to go. And the one that is most common, okay, so this one was used both times, and then the furthest one out, these two are actually in parallel. If I want to, what I can do is I can redraw this circuit, and I can put the junction here and go to this resistor number 2 and come back. Remember, the longer line is positive, shorter line is negative, and then I'm going to just have this come out and I'm going to draw that other resistor. So as long as I don't change where the junctions are, so there's a junction here, I can make this move over to here like it did. Now I can see much better that the 1 is here and that the 2 and 3 are in parallel. So let's do this. Let's go ahead and put in resistor 2 and resistor 3, and then we're going to use our chart to help us. We know that this is in parallel, so we're going to put our bracket here that we've done before. So there's our bracket. We're going to put this, and now we need to find out what is the resistance in parallel. So be really careful, because remember, 1 over resistance in parallel is equal to 1 over the first resistor plus 1 over the second. So this is 1 over Rp is equal to 1 over 2 plus 1 over 3. We need to get a common denominator. That's really easy to do. That would be 3/6 plus, and then here we have 2/6. So we end up with 5 over 6, but that's 1 over Rp, and we just want Rp, so that would be 6 over 5. Don't leave it in a fraction. That won't work. We need to go ahead and divide it. So here our parallel resistance is 1.2. And we're going to put that in here. Now I know that this whole thing right here is 1.2, so I'm going to list that there. And then this whole thing is in series with our 1, so we're going to put our 1 here, and then we're going to put another line so that we have a total column. We're going to put T for total, and we're going to add the 2 since these two things are in series. So 1.2 plus 1 is 2.2 ohms. So that's our total resistance. Our voltage is 6, and if I want to find the current, what I'm going to do is I'm going to write current is equal to voltage over resistance. So that's 6 over 2.2, and then that will give me 2.73 amps. So here we have 2.73 amps. According to the junction rule, so what we're going to do here is we're going to say, we know that the junction rule, so I'm going to write junction here. According to the junction rule, we know that all of these should be the same current. So 2.73 amps and 2.73 amps, because we know that the current going in should be equal to the current going out. So the current coming into this, which is right here, should be the same as the current that's going through both 2 and 3 together. So let's go ahead and find out what the voltage is. 2.73, remember V is equal to IR. Sorry, IR. So 2.73 times 1 is 2.73. 2.73 times 1.2 is 3.28. We also know using the junction rule, so here we're going to, I'm sorry, using the loop rule, we're going to write loop right here and write loop here, that the in a loop, both of these are going to be the same. So that's 3.28, and then this one is 3.28 also. So our 2 ohm resistor has 3.28 volts, and our 3 ohm resistor has 3.28 volts. It's because our parallel branch has that. So now we could talk about the loop rule in our answer. Remember, you have to do more than just give the chart. You're going to have to actually write things out and explain what's going on. If I want the current here, I'm going to have to take 3.28 divided by 2, and I get 1.64 amps. And then 3.28 divided by 3 is going to give me 1.09 amps. But we want power, and remember, power is equal to IV, so I could use that. I could use V squared over R, or I could use I squared times R. All three of those will give me the same thing. But let's do the easiest one, 3.28 times 1.64, and that's 5.38 watts. At that point, we have done what we want. They want to know what the power was in that resistor, and we would stop right here. If you continue on and fill this out, you're just wasting time, so just know that. But if you did need to know what these are and you want to practice, this one's 3.58, this one's 8.95, so it's really almost the sum of these two. This one's 7.45, and then if you add these two, or multiply these two together, you should get 16.38 watts. And that is the end of the notes for the electrostatics and electricity review.